All right, our next part of our discussion, we will look at oscillations and periodic motion. Okay, and we'll try to define some terms for you to give you some working knowledge here. So first off, periodic motion. Any motion that repeats itself over and over. Obviously that name should mean something, right? Periodic means every so often, and motion that repeats itself over and over. Now some terms. First is a period. A period is the time required for one cycle of this motion. Okay, we use seconds as our unit. So a period, just time required for one cycle. Frequency is the inverse of the period. So if period's in seconds, frequency is in seconds over 1. 1 cycle per second is a hertz. So hertz is our unit of frequency in the SI. Some common frequencies in periods. You can talk about clocks, right? How fast the hour hand moves, how fast the minute hand moves. Second hand's probably what we're more familiar with. One period, 60 seconds, which is 1 over 60 is 0.017 frequency. I want to point down to the bottom of the computer. So the period for a computer processor is 3.1 times 10 to the negative 10. You take the inverse of that, and that gives you what's called a gigabyte. 3.2 times 10 to the 9th, so giga. All right. So period and frequency inverses. Here's an example of usage. Walk up a flight of stairs, you take your pulse and observe 82 heartbeats in a minute. So the question is, how frequent is your heartbeat in hertz? So we take 82 heartbeats in a minute. And hertz is per second, so I'm going to have to convert my minutes, 1 minute, into 60 seconds. I just take 82 divided by 60 and I get 1.4 hertz. So the frequency of my heartbeat is 1.4 hertz. What is the period of your heartbeat? Period is 1 over frequency. So 1 over 1.4. And when I do that math, I get 0.71 seconds. So every 0.71 seconds, your heart's beating if your pulse is 82 heartbeats in a minute. Other terms. Simple harmonic motion. This is motion that occurs when there's a force, okay? And this force makes an object go toward equilibrium is proportional to the displacement from equilibrium. So for example, if it starts here and it goes 1 meter away, goes past and goes to another 1 meter away, then we know that it is going to be simple harmonic motion. The restoring force in simple harmonic motion is the force that restores the object to equilibrium. So let's say we had something attached to a spring, and we stretch the spring out and then we release. The spring force is the restoring force that tries to bring it back to equilibrium. Now, simple harmonic motion occurs when the restoring force is proportional to the displacement from equilibrium. Okay, so with a spring, if we had something on a spring, that's what we would see. It bounce back and forth. Simple harmonic motion. Here's a nice diagram from the text. So we take our spring, okay, and it's at equilibrium here. We stretch it out to here. We haven't let go yet, but we're applying a restoring force. When we release, the force, spring force pulls it in. When it gets here, the force is equal to 0. When it goes beyond and goes to the max displacement in the negative x, we have a velocity of 0. It comes back to max velocity, and then back to where we started the first cycle. So a cycle would be down and back. And the time it takes to go down and back, then that would be one of the time it takes to do a cycle. And then the other term that comes up, and this comes up a lot with a lot of things that we're going to do here in the next couple weeks, amplitude. The displacement from equilibrium. So looking back here, when we talk about this displacement from here to here, that would be the amplitude of our simple harmonic motion. So if we were to take this spring and attach a pen to it, and take a strip of paper and move it this way, as the object on the spring goes back and forth, it will draw a line. And if you've worked with math, you'll see this curve has a very noticeable look. It is a sine wave. Sine waves are used to describe simple harmonic motion. So when we look at a sine wave of simple harmonic motion, the top and bottom parts are our amplitude. the middle point here is our equilibrium position, okay? And then time, it will be on the x-axis here, and we can manipulate time. So those of you in calculus can do a lot of work with this. So we have an air track cart. That just means it's no friction. Attached to a spring, oscillates one oscillation every 2.4 seconds. At time equals 0, the cart is here, okay, released from 0.1 meters. And what is the position at 0.6 seconds and 1.2? So the first thing we got to look at is our 2.4 seconds in oscillation. So it goes down and back in 2.4 seconds. So the question is, what is the position of the cart at 0.6? Well, if I take 2.4 and divide it by 0.6, I get 4. All right, so it's going to be 1/4 of the way. So if I break this up, I go, here's 1, here's 2, here's 3, here's 4. So to go 1/4 of the way would be to 0. So after 0.6 seconds, we're at 0 meters. At 1.2 seconds, 2.4 divided by 1.2 is 2, so we're going to be halfway. So I go 1, 2. At 1.2 seconds, we're at negative 0.10 meters. Really no math involved here, just some logic, but you have to know what one oscillation is time-wise. So we can also figure period if we know some things about the spring system. If we know the mass that's hanging from the spring and we know the spring constant, we can also find the period of a mass spring system. And hopefully we'll have a chance to look at that. But the units of this period, of course, are seconds. But it's 2 pi times the square root of mass divided by spring constant. So we have a 0.22 kilogram air track car attached to a spring with a constant of 12 newtons per meter and set into motion. What is the period of its oscillation? Okay, so same thing we saw right here. Okay, but our information is mass and k, and we want to find period. Period essentially is 2 pi square root of mass over k. 2 pi square root, my mass is 0.22 kilograms, and my k is 12 newtons meters. And then when I do all this math out, I get 0.85 seconds. And that's the period of oscillation that we would see with this system. So let's take a look at just a regular graph here, sine curve of mass versus spring, mass in the spring position versus time. And let's compare. Let's say we increase the spring constant by a factor of 4. We increase k. You see our waves get closer together. Frequency doubles, period is halved. So if we increase the spring constant by 4, our period is halved. The time is cut in half for one oscillation. Let's say this, let's go to B, increase mass by a factor of 4. Compare the graphs. If we increase mass by a factor of 4, frequency is halved, so the period doubles. So we double the period if we increase the mass by a factor of 4. Here we're going to change. The change is going to be increased spring constant and mass, both by a factor of 4. If we increase both by a factor of 4, the graphs are exactly the same. Okay. What if we increase amplitude by a factor of 2? So we're increasing amplitude. Frequency and period remain unchanged. All right. Speed and acceleration increase, but frequency and period remain unchanged. So if we look, only thing that when we change amplitude, we change speed and acceleration of the mass, not the period. Just some things that could happen with the spring system, and again, we'll look at some of those. One last math problem. 0.1 kilogram mass attached to a spring. The spring stretches by 0.2 meters. Find the period of motion when this mass spring system oscillates. Okay, so on paper, the first thing we would do is we got mass spring, we want period. Let's do this. Problem is we know mass, but we don't know k. So we have to find k. So we got to go back to Hooke's law. Force is equal to kx. All right, since we're talking a spring mass system, we know what our force is going to be. Force is going to be mg. K is k. X is x. Our mass is 0.1. We'll assume we're on Earth, 9.8 for G. K we don't know, but our X is 0.2 meters. When we solve for K, we get 4.9 newtons per meter. Now that I know K, I can substitute it into here. My mass is 0.1. Now I can solve, right? I got 0.1 over 4.9, take the square root, multiply by 2 pi. And our period is 9 seconds. So, moral of the story, if we get stuck trying to find a period of a spring system, and this spring is going to be affected by gravity, which is usually the case, we got to go back to Hooke's law. mg equals kx. And we can work our way through that.